In the last tape, we talked about the function of the input sensors and what they tell the onboard computer, the ECM. But what does the ECM do with this input data? How does it evaluate it? That's what we'll discuss in this section. Simply put, the ECM analyzes information from the input sensors and uses it to operate the various output controls. The purpose of the output controls is to provide efficient engine operation and help achieve our goal of good emission control and fuel economy. The 7 principal output controls we'll be covering are the mixture control solenoid, air management system control, idle speed control, canister purge control, transmission converter clutch, early fuel evaporation, and exhaust gas recirculation. Together, these output controls make up a complete system of engine performance management. The first output control we'll go over is the mixture control solenoid, located inside the carburetor. There are 2 basic types of mixture control solenoids, the type found in the dual jet and quadrajet carbs, and the one located in the varijet carb. Although both work basically the same way, we can only show you the dual jet and quadrajets because the varijet type unit is completely enclosed, making it impossible to properly demonstrate the moving parts. Essentially, the mixture control solenoid works just like a starter solenoid. It operates through being energized by an electrical signal. When system voltage is added to the solenoid, it is routed through the ECM, which then decides at what point to energize the solenoid based on carburetor needs. More specifically, the MC solenoid affects the operation of certain carburetor parts, including the spring, the plunger, which has a paddle attached to it, and 2 metering rods underneath the paddle. The way these work is that when the MC solenoid is energized, it pulls the plunger down against the spring, while the paddle pushes the metering rods down, thus creating a lean air-fuel mixture. When there is no current flowing through the MC solenoid, the spring pushes the plunger back up. The springs do the same to the metering rods, giving us a rich air-fuel mixture in the carburetor. The computer decides how long it will turn the solenoid on, and as we've mentioned before, the ECM makes this decision 10 times a second. We can demonstrate what's happening in the MC solenoid through the configuration or shape of this line. It represents 1/10 of a second, or the distance from here to here. First, we place a test lead connector on our test engine, which has a green test connector attached to it. If we hooked a very expensive laboratory scope to it, we'd get a picture much like this one, representing a 0 voltage flat line. Horizontal lines indicate a time period, in this case 1/10 of a second. Turn the MC solenoid on, and you've got a line like this. The plunger and paddle would be down for almost a full 1/10 of a second, resulting in a lean air-fuel mixture. If the ECM shut down the power to the MC solenoid, this kind of line would appear for 1/10 of a second. The paddle would be forced up by the spring, and you'd have a rich air-fuel mixture. However, there is one exception. If you're running in the power enrichment mode, the computer would shut down the MC solenoid, and you'd see a full, rich, flat line up here. To see what's going on inside the carburetor, we can simply hook up a dwell meter to the test connector. The dwell meter measures the time when current is flowing and tells us if the carburetor is running rich or lean. Once the dwell meter is connected to the test lead, we set it on a 6-cylinder scale. It doesn't matter how many cylinders the engine has, because the 6-cylinder scale provides us with a 0 to 60-degree meter reading. Now, with the engine running, and considering 60 degrees as a full 1/10 of a second, we can see what the on time is in the solenoid. 0 degrees per 1/10 of a second on the dwell meter indicates no on time. The paddle would be up all the time, and you'd have a full rich condition. A 60-degree reading per 1/10 of a second gives you continuous on time. The paddle would be down all the time, and your mixture would be full lean. 30 degrees is the midpoint, and on a properly calibrated carburetor, this is the ideal running condition, or as we've said before, when there is an optimum air-fuel ratio of 14.7 to 1. Under actual driving conditions, it's impossible to achieve a constant 30 degrees dwell in closed-loop operation. The closest we can come to the oil is a nice, even float above and below the 30-degree point on the meter. But this is still more than sufficient to maintain optimum fuel performance. If you're down here or up here floating, something is wrong. A fixed meter reading indicates the system is in open loop, and the ECM is controlling fuel mixture based on coolant temperature. This diagram shows the position of the mixture control solenoid inside the carburetor. Solenoid adjustment is made by a lean stop screw, which controls how far down the paddle will travel when the solenoid is engaged. There is also a rich stop screw adjustment that controls how far the paddle can go up when the solenoid is de-energized. So far, we've talked about controlling the metering rods and the air-fuel ratio in the main metering system. But it's also important to know about the idle air-fuel adjustment. Conveniently, that control sits on top of the paddle, so the plunger and idle air bleed can travel up and down simultaneously. The end result, after all adjustments have been made, is a carburetor that should operate at a 14.7 to 1 air-fuel mixture at 30 degrees dwell. The next output control we want to talk about is the air management system. There are 3 types of air management systems. 2 of them pump air with an air pump through the air management valves to the exhaust. The 3rd type, called the pulse air injection reaction system, is found mostly on smaller 4-cylinder vehicles and is located in the exhaust manifold. This system uses natural alternating vacuum pressure pulses to pull air into the exhaust through the check valve. When the vacuum pulse shuts down, the check valve closes so the exhaust doesn't get back into the air cleaner. Although there are over a dozen different part numbers, there are basically just 2 types of air management valves, a 3-hose system and a 2-hose. The 3-hose system has 2 electrical solenoids and, naturally, 3 hoses. 1 hose goes on the catalytic converter, 1 to the exhaust manifold, and the last to the air cleaner. To avoid confusion, make a note that the hose to the exhaust manifold may divide and run to both sides of the engine, but it is still counted as just 1 exhaust manifold hose. The 2-hose system, on the other hand, eliminates 1 of the hoses to the catalytic converter and 1 of the solenoids. If you see a 3-hose system, the vehicle has a dual bed converter, with the 3rd hose going down to add air to the converter oxidizing bed. A 2-hose system indicates a single bed catalytic converter. No matter which kind of hose system a car has, both types serve the same function. They allow air into the exhaust manifold. When the air meets hydrocarbons leaving the engine, the combustion continues raising the temperature to warm up the oxygen sensor and help it to reach 600 degrees to start operation. The combustion also warms the catalytic converter to clean up some emissions before the system goes into closed loop. Computer control is necessary because too much oxygen being pumped in would disrupt operation of the oxygen sensor. And a false reading by the oxygen sensor would tell the ECM to compensate for an air-fuel condition which doesn't exist. Consequently, in closed loop, it is imperative that we get the air out of the exhaust manifold and through the air cleaner. In a 2-hose system, this is accomplished by an electrical signal from the computer to a diverter valve. In a 3-hose system, we stop sending air to the manifold and switch it downstream to increase the efficiency of the oxidizing bed of the catalytic converter. This gets us well past the oxygen sensor and eliminates the possibility of false signals. If you go into wide open throttle operation, the ECM will signal the system to divert the air out through the air cleaner. This prevents overheating and meltdown in the oxidizing bed of the converter. The same signal to divert it is also sent when the engine turns at over 2,500 RPMs. Whether a car uses a 2 or 3-hose model, both valves perform the same job as the diverter valve found on older cars. It prevents backfire in the exhaust during coasting conditions. In the previous tape, you saw this module when we talked about input sensors. Now we'll examine it in greater detail. This is a basic 4-terminal module called an HEI, GM's acronym for High Energy Ignition. The computer commands this module in order to control ignition timing on cars with electronic spark timing. This is a simple schematic of the GM 4-terminal HEI module. One of the most important components in the module is a pickup coil, which provides RPM and crankshaft data to the ECM. The way this works is that the pickup coil sends out a pulse signal which triggers a switching transistor that replaces ignition points. The end result is that instead of the points opening and closing, we now have a much more dependable transistor to do the job. Timing is controlled by the pickup coil through vacuum advance and centrifugal advance. If anything changes at the pickup coil, the ignition time will change accordingly. When electronic spark timing is added to the diagram, a 7-pin module is created. Note this line coming off the signal converter. It sends an HEI reference signal back to the ECM and gives it the proper RPM and crankshaft position information. This is also sometimes called a tach signal. When the computer sees a signal over 200 RPM, after a 5 to 15 second startup delay, it will send out a 5-volt bypass signal and take control away from the pickup coil. From this point on, the ECM controls the ignition coil. It receives data on barometric pressure, RPM, manifold vacuum, and coolant temperature, then uses this information to control the ignition coil trigger signal and set ignition timing. However, it's precisely because the ECM controls the ignition coil that you must remember to take control away from the ECM when you start out to set base timing. This can be accomplished on most carbureted vehicles by simply finding the 4-wire connector. It should be coming right out of the distributor, and unplugging it. That will get you back to the basic 4-pin module function where the pickup coil controls the switching transistor. It's important to note that some cars won't run if the connector is unplugged, while other types of cars need to be grounded. The easiest thing to do is check the tune-up information tag under the hood. It will tell you exactly how to set the base timing and what it should be set at. We also recommend that you follow factory specifications for base timing. It's been our experience in checking cars on a dynamometer that factory specs work best because the computer has been programmed for them. Another output control that's mounted right on the carburetor is the idle speed control motor, or ISC. Like a power door lock motor, the ISC uses a reversible current motor. Energize the ISC with one polarity and the plunger will extend. Reverse polarity and the plunger will retract. When a car is equipped with an ISC motor, the computer is in control and there are hardly any idle speed adjustments you can make. The one exception is changing the minimum and maximum authority, or in other words, modifying the extreme ends of the ISC's operating range. To make these adjustments, you need to energize the motor through terminals C and D. They're the ones closest to the ISC motor. Put 12 volts across C and D, and the motor will go one way. Reverse the terminal, and it'll go the other way. But try to be careful when you do this. If you accidentally throw 12 volts across A and B terminals, you'll fry the ISC throttle contact switch, a mistake that could wind up costing you over $100 to replace it. Two last things to keep in mind. The ECM controls idle speed based on RPM, AC clutch operation, transmission selector lever position, power steering pressure, and coolant temperature. It also overrides other inputs if the car overheats or system voltage is too low. This is important to remember because an overheated engine or low voltage condition would make the computer send the ISC motor a command, forcing it to boost idle speed to build up charge in the system or increase coolant flow based on temperature data. The ECM also controls canister purge in the evaporative systems. Evaporative systems have been on cars for the last 15 years or so, and they perform vital functions in cleaning up emissions. The canister system takes care of about 20% of the pollution, and the PCV valve another 20%. Together, these two simple elements do almost as much work as the rest of the system. That's why it's so important to have a properly working canister. When the engine is shut down, the canister collects fuel vapor from the engine and fuel lines. We don't purge these vapors into a cold engine because this could create drivability problems and defeat the emission control functions. Because of these potential problems, the computer looks at coolant temperature and controls a valve that allows the canister to purge properly only after the engine has warmed up. When the engine is warm and in closed loop operation, The ECM sends a signal to turn the purge valve on, drawing air up through the bottom of the canister and sending fuel vapors back into the engine. The oxygen sensor then reads this rich condition, and the ECM sends a lean command to the carburetor to balance the air-fuel ratio. There are some engines which don't use a computer-controlled canister purge valve, but even these are set to operate above closed-loop temperature levels and use a thermostatic vacuum switch that functions on coolant temperature. Of all the outputs we've talked about so far, the transmission converter clutch operation may be the most demanding on the computer. To activate the transmission converter clutch solenoid and provide efficient converter clutch operation, the ECM must read and evaluate data from no less than 6 different input sensors: the coolant temperature sensor, the park neutral switch, the brake switch, the vacuum sensor, the throttle position sensor, and the speed sensor. When activated by the ECM, the TCC solenoid connects the flywheel directly to the output shaft of the transmission through the torque converter. The early fuel evaporation system, EFE, is also controlled by the ECM based on coolant temperature. There are 2 types of EFE systems: a vacuum-controlled heat riser and a heated grid. As you know, heat risers have been around for a long time, but we've made one modification. We've added a vacuum motor which forces it closed with engine vacuum when the engine temperature is low. After the engine warms up, the ECM controls a relay that releases vacuum and the valve opens. The second type, the heated grid, is located right below the primary bore of the carburetor. The grid gets warm with only 12 volts of current and heats up the air-fuel mixture, thereby improving atomization of the fuel. This grid is also controlled by the computer based on coolant temperature. The final output control we want to mention is the EGR valves, or exhaust gas recirculation system. To start with, we don't want the EGR working on cold engines because it causes a whole variety of drivability problems. Once again, based on coolant temperature, the computer sends a command to a relay which operates the EGR valve. Having received this command, the valve uses vacuum to recirculate the exhaust gases. One important thing to always keep in mind is the EGR valves, or exhaust gas recirculation system. To start with, we don't want the EGR working on cold engines because it causes a whole variety of drivability problems. Once again, based on coolant temperature, the computer sends a command to a relay which operates the EGR valve. Having received this command, the valve uses vacuum to recirculate the exhaust gases. One important thing to always keep in mind is that the coolant temperature sensor and the oxygen sensor are at the heart of the 3C system. So make it a point to check these 2 sensors every time you're faced with servicing a vehicle with computer command control. That completes our review of the major output controls. As was the case with the inputs, we don't have the time to go over other important elements like the air conditioner compressor clutch, engine cooling fans, and electronic fuel pumps. But don't worry, there are written materials to provide you with the necessary information. We suggest you watch this tape more than once if possible and review previous materials. In the future, we'll be getting into even more detailed diagnostic procedures, and a solid base of understanding will only make it easier for you to take advantage of this advanced technology and to profit by it. In previous tapes, we introduced you to the basic theory behind computer command control and identified the major inputs and outputs. In this tape, we'll turn theory into practice and show you how to solve potential problems with trouble codes stored in the computer memory. It's important to keep in mind that anything we cover relating to service begins with one basic premise: the engine must be in reasonable operating condition. What do we mean by reasonable operating condition? Simply put, it means acceptable compression, spark, and fuel delivery. After all, you can't resolve a computer control problem if the fuel pump or carburetor is malfunctioning. We'll start our study of diagnostics by examining the General Motors stored trouble codes and service manual procedures. You'll learn how to read them, what they mean, and how to use the diagnostic charts to resolve a problem. The first thing to do is a visual check. You'd be amazed at how many problems can be solved with this simple service procedure. Here's why. As you may recall, the 3C system reads information sent to it from the sensors in the form of low electrical signals, then transmits this data to the ECM. A loss of even 1/10 of a volt can distort the information the ECM is receiving and acting upon. That's where the visual check comes in. It provides an easy way for you to locate the cause of voltage-reducing situations. You'll find the major cause of voltage-reducing problems is poor connections. The most obvious type of poor connection is where the circuit is broken, but this is relatively uncommon. A more frequent problem is the poor connection which allows moisture to seep in, causing corrosion, and thereby adding to the resistance in the circuit and changing the voltage traveling to the ECM. GM has attempted to minimize the potential for voltage-reducing problems with their positive latch-type connectors. When conducting your visual check, you should always look for open latches. Weather pack seals also help prevent voltage-reducing situations. Essentially, weather pack seals are moisture-proof silicone seals which keep the circuit intact. They're found in the connector where the wires run into it and where the connection is made. These seals, combined with the positive latch, are usually enough to prevent any problems, unless, of course, they've been tampered with. Tampering can mean a lot of different things. It could occur from accidental damage in the service bay, or even from a customer working on his car himself. In any event, when doing system voltage checks, be careful not to back probe at the connector, or you could accidentally tear up the seal and allow damaging moisture to defeat the system performance. Another thing to look for in your visual check is poor or improper grounding. There may be 3 or 4 ground wires, all terminating in a bolt, screw, or lug in the engine compartment, and they can get loosened or damaged or corroded over time. So check to be sure the system is properly grounded. Having completed the visual check steps, we can now turn our attention to the actual diagnostic procedures. The General Motors diagnostic procedures consist of 3 phases: diagnostic circuit check, driver complaint sheet, and system performance check. This little chart gives you a preview of what we'll be covering. Step 1, the diagnostic circuit check, means you go to the computer and see if there are any trouble codes stored in its memory. If there are, the ECM will give you a trouble code number. This number matches a chart with specific instructions for correctly identifying the problem. Step 2, the driver complaint sheet, is used when Step 1 fails to reveal any trouble codes or when no repair is called for after following the chart. Like Step 1, the driver complaint sheet has a chart to follow so repairs can be made. Step 3, the system performance check, is done after any repair is made or when no problem can be identified from working Steps 1 and 2. If no problem is found after a system performance check, then you can usually conclude that the car is in proper working order. Now that you understand what each phase entails, let's examine them more closely. Before starting with Step 1, the diagnostic circuit check, you first need to make sure the check engine light works. We'll demonstrate this procedure on our test engine. Turning on the ignition switch, but not starting the engine, should cause the check engine light to go on. If it doesn't, stop right there, because you can't check the diagnostic circuits without the light. To solve an engine light problem, consult your various manuals for complete instructions. Assuming the check engine light does work, you can now begin the diagnostic circuit check. First, you locate the assembly line data link, or ALDL. It's also sometimes called the assembly line communications link, but ALDL is more common. On most cars, the ALDL is found either to the right or left of the steering column under the dash. In 1981 model cars, a 5-terminal connector is used. Although this was changed to 12 terminals in 1982 in newer cars, they still use 5 terminals on the top row with carbureted engines. To check for stored trouble codes, you take a spade lug or jumper wire and go from this terminal to this one on the connector, or from here to here on the 12-terminal model. Essentially, all we're doing is taking this wire to ground. When properly grounded, the computer will go into its diagnostic mode. You'll know the ECM is in a diagnostic mode because the check engine light on the dash will start flashing. If it is not flashing, make sure the wire you're grounding is white with a black tracer, because sometimes a unit will come from the factory with that wire in some other position than it should be. You should also check to see that the light does not go on in a proper ground. If for some reason the ground is not good, you may want to ground the unit to the door jamb switch. If the light does go on when the door is open, you'll know that both the switch and your ALDL is properly grounded. In this situation, also make a note to find out why the factory ground wasn't functioning in the first place. With proper grounding and the ignition switch on, the check engine light should be flashing the following sequence: 1 flash, pause, then 2 flashes. It will flash this sequence of 1, 2, a total of 3 times, and it's called a trouble code 12. It tells you the ECM has diagnostic ability. A trouble code 12 also indicates that the computer is not receiving a distributor reference pulse, or more simply, any RPM information. But this is only logical since the engine is not operating. Most of all, remember that trouble code 12 is the only code that doesn't store in the computer. It goes away when the engine is started. Just as the 1-2 flash of code 12 indicates diagnostic capability, other flash sequences indicate other trouble codes. For example, 2, then 3 flashes is a code 23, while 3, then 2 flashes is a 32 code. As you can see, the first flash is the first number of the code, and the second flash is the second number of the code. As you watch the check engine light flash code numbers, you'll want to write each of them down. And no matter how few or how many codes have been stored in the computer, the sequence will always begin and end with the 12 code repeated 3 times. This is to let you know that you've seen all that is stored in the memory. To give you an idea how this would work in the real world, we've stored some trouble codes in the ECM of our test engine. The ALDL on the test engine has been moved up here, since we don't have a dash to put it behind. It is the 12 terminal type, and we've jumpered these 2 terminals. Now, let's see what the computer tells us. We see a 1 flash, 2 flash sequence, a 12 code, which indicates the computer has diagnostic capability. Next, we check to see what other codes are stored. Like the 12 code, each will repeat 3 times. There are 2 flashes, then 3 flashes. We have a 23 code. Anything else stored? Yes, 3 flashes, then 2 flashes. A 32 code. Now a 4 and 1 flash. A 41 code. And there's our 12 code again, signaling that we've read all the codes stored in ECM. At this point, the entire code sequence will repeat until we stop it. If this were a customer's car, you would have written down the code numbers, then turned off the ignition, erased the computer memory, and prepared to take the vehicle for a test drive. Before we continue, let's take a look at how you clear the computer memory. There are 3 ways to do it. The first way involves removing battery voltage to the computer by disconnecting the battery. But it is not recommended because it not only clears out the memory, it clears out any other memory circuits you have in the vehicle, like radio presets, power seat settings, and trip computer. A better way to clear the memory is turning off the ignition, then going to the fuse block and removing the fuse marked ECM battery. This will power down the computer and clear the memory. You'll find that some cars have 2 fuses, one marked ECM battery and the other ECM ignition. You may want to remove the ECM battery fuse. The third way, and the one we recommend, is to go to the ECM and completely disconnect the cable. To be certain the memory is cleared, you'll want the unit unplugged for about 10 to 15 seconds. This technique not only results in breaking and making a new connection, but also gives you the benefit of a fresh, clean ECM hookup. However you clear the memory, the ignition switch must be off. Once you've cleared the memory, you can now take the car for a test drive. And you must travel at highway speeds for at least 5 minutes in order to record possible trouble codes in the memory. After completing your test drive, you'd go back to the ALDL, ground the circuit, and prepare to record codes stored in the memory. Repeating the code check step may be the most important time you spend in your diagnosis, because it can reveal what is called false trouble codes. Here's an example of what can happen. Let's say that after returning from your road test, you turn on the ignition, see a 12 code which indicates diagnostic capability, and it is immediately followed by another 12 code sequence. The obvious question is, what happened to the other codes that were previously stored in the computer? The answer is that the trouble codes you erased in the memory are supposed to return during the test drive. But if they don't return, then this tells you that they were false trouble codes and there's no real malfunction. False trouble codes can be the result of many things. Most often they occur because of a repair or service function performed at an earlier time. For example, a mechanic does a tune-up with a part disconnected. This in turn causes a trouble code to be recorded and stored before the part is reconnected. Although everything is as it should be, the trouble code is in the memory until purged. Discovering false trouble codes before you do any serious work not only saves you time, but also saves the customer considerable money for parts you would have ordered but never needed. In short, it is our experience that stored trouble codes happen often enough to make the test drive after erasing the memory a vital part of your service program. For the purposes of our discussion, let's say that after the test drive, all the stored trouble code numbers were still in the computer. This would indicate actual trouble codes, and you'll want to deal with each of them in numerical order, starting with the lowest, code 23. Looking on the list with a simplified description of each trouble code, you'll find that code 23 is an open or grounded mixture control solenoid. You then go to chart number 23 and follow the steps in the exact order they're listed. Do not skip around and do not omit any steps. These diagnostic procedures only work when they are done precisely as indicated. The first thing the chart tells you to do is check connection at mixture control solenoid. If nothing is wrong, clear the memory and recheck for code 23. The chart says that if the code does not come back, the circuit is okay. For now, let's say the code did come back. In this case, you move on to step 2 of the chart. Step 2 says to check voltage at the mixture control solenoid dwell lead. This is done by turning the ignition on without starting the engine. And remember, the test terminal should not be grounded at this time. Next, you take the meter and prepare to test the engine when the solenoid has stopped cycling, or after 25 seconds. 25 seconds is specified because ordinarily, if the engine hasn't been started within this amount of time, the computer will shut down the MC solenoid. You'll notice that our test engine is set up a little differently. It won't cycle at all until after it has been started. GM wants us to measure the voltage when the solenoid is not cycling. So we'll take our meter over here, connect it to the dwell lead, and ground the meter somewhere over here. The meter shows 12 volts. We look at the chart and find there are 2 options, under 10 volts or over 10 volts. We're over. So we go on to the next box. Check voltage at ECM terminal 18. To get to terminal 18 on the ECM, take your meter inside the car, usually on the right-hand kick panel. On the test engine, the ECM is right out here where we can reach it. The terminal at the ECM can be back probed by lifting away the plastic wire covering. There is no weather pack seal to worry about damaging, so it's okay to take a little screwdriver and back probe at terminal 18. The meter again shows us 12 volts. And again, there's a choice of under or over 10 volts to determine the next procedure. We find that the next step is to check mixture control solenoid resistance at the carburetor. To accomplish this, we first disconnect the mixture control solenoid from the carburetor. Then, switch the meter from volt readings to ohm readings and check the solenoid resistance. The meter shows an MC solenoid resistance of 23.4 ohms. Looking back at the chart, we see we have a choice of under or over 10 ohms before proceeding to the next step. We're over, so the next box says, check voltage from ECM terminal 21 to ground. We now have to go back to the ECM and locate terminal 21. Switching the meter back to a volt scale, we back probe terminal 21. Our choices this time are under or over 4 volts. We're over, so we drop down to the last box on the chart. It tells us that our problem is either a faulty connection or the ECM itself is defective. Checking the ECM connection, we find that it's in good shape, which indicates that the ECM itself is in need of repair. After resolving the code 23 problem, we would move on to the next code on the list, code 32. Once again, it's necessary to follow the instructions on the chart for a code 32 until we've reached a satisfactory solution. We could then go on to the next code, code 41, and do the same thing. We would proceed in this manner for all the trouble codes stored in the ECM memory, taking them, as we've said, in numerical order. However, there is one exception. If you find a 50 series trouble code stored, remember to do that one first. Trouble codes in the 50 series indicate a problem with either the ECM or the PROM. And you want to resolve these types of problems first because a defective ECM or PROM can be the cause of the memory storing false trouble codes. Consequently, when you're checking your diagnostics, remember to record all numbers in the memory. Then make any 50 series code repair. Clear the computer memory and do a road test. Finally, check to see if any of the other trouble code numbers you noted are still in the memory. Often the 50 series problem is the cause of the other false codes being stored in the computer. The second phase of the GM diagnostic procedure is based on the driver complaint sheet. This step is used when the customer has made a specific performance complaint. Our check of the diagnostic circuit has come up with no stored trouble codes. Once again, remember that everything you need to know to perform a thorough diagnosis is listed on the driver complaint sheet. For example, let's say our customer has a complaint, but no check engine light is showing. In this instance, you would perform the same basic checks you've been performing for years on cars without computer systems. After all, a properly operating engine is vital to the diagnosis of any problem. Another situation you might come across is a combination of check engine and battery or temperature lights. In this case, you'll want to check the other warning lights before you start to deal with the check engine situation. Yet another problem you may encounter is seeing an intermittent check engine light without having any trouble code stored. If this happens, check for intermittent connections from various points shown on the complaint sheet. As you can see by reading down the sheet, a variety of possible solutions is offered. Some in the form of direct action, others as references to particular charts which will lead you to a solution. These charts work in exactly the same manner as the trouble code charts you saw earlier. But what happens when you've gone down the list and can't find the specific driver complaint your customer has brought you? That's when you need to take note of the last point on the sheet. Make system performance check on warm engine. This is the third phase of the GM diagnostic procedure. Although the system performance check is the ultimate diagnostic tool in the GM plan, it is not just a when all else fails approach. It's a worthwhile procedure which should be implemented after making repairs dictated by either of the other two diagnostic methods. The system performance check may sound complicated as we go through it, but it's sure to become second nature as you begin to use your new computer service skills. To implement the system performance check, you'll need tack and dwell meters, plus a jumper wire or two. As you'll see in the chart, there are a couple of things you have to do to get the check started. And be careful to follow these steps in order. Changing the sequence, as we've mentioned before, will give you incorrect data and prevent you from solving your problem. Here's a good example of how one little mistake can blow the whole procedure. Following the check procedure chart, you'll first start our engine, then ground the test terminal. But if we ground the test terminal before starting the engine, we can forget about the rest of the steps because anything we do will result in an inaccurate reading. The right way to proceed is to start the engine, ground the test terminal, then disconnect and plug the canister purge system hose. For purposes of the test, we don't want fuel vapors running back into the system. Now that the tack and dwell meters are handy and ready to go, we unhook the mixture control solenoid from the carburetor and ground the MC solenoid dwell terminal with the jumper wire. Next, run the engine up to 3,000 RPMs. Then, reconnect the MC solenoid. The engine should be running at a full, rich mixture when the solenoid is connected. Make note of the RPMs. The engine has now gone to a full lean mixture. You'll notice a variation in RPM shown on the tack. We match the variation we are seeing to one of those two boxes on the chart. If the variation was less than 300 RPMs or even increased, we'd be following this path to a solution. But since the RPM drop was greater than 300, we need to proceed to the next box down for instructions. First, connect your dwell meter to the MC solenoid dwell terminal. Then, set the meter for the 6-cylinder scale, regardless of how many actual cylinders you're working with. At this point, you want to set the carb on the high step of the cam and run the engine for 1 minute or until the needle on the dwell meter starts to vary, whichever comes first. Once the meter starts to vary, or 1 minute elapses, then return to idle and make note of what the dwell meter is showing. The next step is to match your meter reading to one of the 4 boxes shown on the chart. Since the meter is not fixed, you can skip these 3 boxes. And because our dwell was varying, you'll want to continue by checking the dwell at 3,000 RPM. As you can see, at 3,000 RPMs, the dwell was in the range of 10 to 50. It wasn't under 10 or over 50, so you follow down the chart and are told to check the air management system. Inspecting the air management system is a very simple procedure. On the test engine, there's a 3-hose system. With the engine off, you won't be able to feel anything in the hose. When the engine is started and is in open loop operation, you should feel air being pumped to the exhaust manifold. When the computer switches to closed loop operation, you should feel the air switch to the catalytic converter. When the MC solenoid is unhooked, the air should switch to the air cleaner hose. If these 3 things take place, then you know the air management system is working properly. The chart then tells us to clear the memory and put the car back on the street. It is now in proper working order. That completes the 3rd phase of the GM diagnostic procedures. Although it works in the majority of situations, you may still find a customer complaining about a drivability problem that didn't show up when conducting the system performance check. We'll get into how to handle these situations in our next tape. For now, just make sure you have the GM diagnostic procedures down pat. And soon, you'll be on your way to becoming an expert in diagnosing and correcting computer command control problems.